New analysis of Marsquakes, which are similar to earthquakes, could offer clues into how Mars has evolved over billions of years, according to new research from the Australian National University and the Chinese Academy of Sciences. For more, Professor Hervoje Tolcic is beaming in for a deep dive.
21 years online. From Star Trek to science and space. And we're not stopping. This is Talkin' Science.
Professor Tolcic, thanks for your time. Can you take us through the phenomenon known as the Martian dichotomy, please?
Well, first of all, thanks for having me. Martian dichotomy is probably one of the largest questions, open questions or mysteries of the solar system. And simply speaking, dichotomy means that Mars has two different parts. And in this case, sometimes you will find the term hemispheres, but it's not exactly the hemispheres. It's a 2/3 of southern part of Mars, the so-called southern highlands, and about 1/3 of the northern part, northern lowlands. That's what the difference is. The southern part being something like 5 to 6 kilometers higher in elevation than the northern part. But apart from that, and these are the obvious these are the something that Voyager observed. So we could call it more transparent than, say, the dichotomy thickness of the Martian crust, which is more subtle geophysical data in this case. So the dichotomy is not only elevation, but also in thickness of the crust, the part being much thicker than the northern part. And on top of that, dichotomy in this context means the difference in the magnetization of there's definitely much more observed in the southern part than in the northern part of Mars.
And there are two hypotheses trying to explain the origin of this dichotomy. Your research lends credence to one of them, that convection is the driver for this vast difference?
Yeah, as you know, there are two hypotheses that are, I would say, most prominent in the community. One of them is the so-called exogenic hypothesis, which basically means that either a giant impact or a series of smaller impacts created that dichotomy. And the other one is endogenic hypothesis, which states that probably the internal dynamics of Mars, either in the form of mantle convection or similar, would cause the differences in Mars that we observe today. So endogenic on one hand and exogenic on the other hand. And our findings in this most recent paper support the endogenic cause because, simply speaking, we observed by using seismic waves, and we will probably get to this, we observed this difference between the two parts of Mars, the southern one being hotter than the northern one, which leads us to conclude that at least from the seismic data, the cause is most likely endogenic rather than exogenic.
Well, we're getting a deeper understanding of the southern hemisphere thanks to rover missions like the InSight lander, but I didn't realise that we know comparatively little about the south compared to the north. Why is that?
Well, that's a very good question, and that's because so far the most recorded Marsquakes have been from the northern part of Mars, and whereas the lander itself is very close to the dichotomy border. So at least from the seismic data, we knew much more about the northern part. But in this new study, we locate 6 Marsquakes in the southern part. And that basically gives us an opportunity to compare our findings from the seismic waves that sampled the southern part of the dichotomy with the northern part. And that's what we did in this recent work.
Well, this is a continuation of your work along with colleagues on data from InSight over the last couple of years. How valuable has that lander been in listening to the heartbeat of Mars?
Yeah, well, I would say this mission will serve as a prototype for many future missions to come, simply because it has been so successful. First of all, the fact that we recorded 1,300 plus Marsquakes from a single mission is just fantastic, and I think no one anticipated that the number of Marsquakes will be that large. When you think about Voyager and the fact that it didn't record a single credible Marsquakes, this is a huge success due to the hard work of the large number of people. Now, I'm not myself, and my colleagues are not a part of the InSight team itself, but we worked on the data independently. It has been, at least in the geophysics community and in the seismology community, it has been customary to release data for everyone to use it. So it's just fantastic to have access to the broadband waveforms recorded by InSight and be able to do this work. And maybe I would say that the global seismology, which is my field of study, at some stage or at some point becomes a planetary seismology, because we apply all the techniques that we develop on our home planet to other terrestrial planets. And we are very excited with the future missions to the moon, and where we will be able to use the same techniques that we applied on Earth and in this case on Mars.
How hard is it to distinguish a Marsquake in the data that we receive back from the lander? What does that data look like?
There's all sorts of data, but first, I should say it's a continuing recording for about 4 years in this case that
Wow.
InSight was operating, and its seismometer called SEIS was operating for that time. And at first, we observed several classes of events. Um, we call it events before we are 100% sure they're Marsquakes. But as you know, I can immediately think of two um, most distinct classes of events on Mars, and one of them are Marsquakes, and another one is impact events. For impact events, we have orbital cameras, and you can think of them as the ground truth events because we know their location. Marsquakes, we have determined in something like 300 plus papers that have been published on InSight data so far that there are basically three classes of Marsquakes. The so-called long period or low frequency Marsquakes, high frequency Marsquakes, and ultra high frequency Marsquakes, or super high frequency. So the low frequency Marsquakes are most similar to the earthquakes that we are well familiar with and that are well documented. The high frequencies are still, I would say, a bit shrouded by mystery because they're probably due to the scattering of seismic waves in the shallow part of the moon. And the super high frequencies are thermally related. So they have a thermal cause, as you know, due to the huge differences in the temperature on Mars. So what our recent study that we used to shed some new light on the dichotomy we use the low frequency Marsquakes. We also use the low frequency Marsquakes to measure the Martian core or its radius, and to study the characteristics of Marsquakes in general. So there are not many of them. There are maybe few tens of these low frequency Marsquakes. Most of them are high frequency and super high frequency events. So I would say, in a nutshell, the most useful for us are low frequency Marsquakes and also impact events due to the meteorite impact.
A couple of years ago, when you released another study, you noted that the likely cause of the Marsquakes is volcanism. That means that the mantle's on the move. How can we prove that?
Well, it's very hard to prove that. There's still an ongoing debate whether the most Marsquakes we observe are of a purely tectonic origin, or there's some volcanic or magmatic component to them. So that's very hard to prove, but some observations that we have made, the observations of the so-called repetitive events, indicate that they're very similar to some of the volcanic events that are observed on Earth. So simply based on the behavior of the so-called repetitive Marsquakes in this case, or their cyclic behavior, we can compare them with the known mechanisms on Earth that are well documented and well studied. For instance, the repetitive waveforms that we detect using our seismological techniques are a characteristic of volcanic events that are basically there due to the motion of magma through the interior of the Earth, in this case, the interior of Mars. So you have an ongoing process of pressurization of volatiles and the degassing that can cause some of the repetitive tremors that we basically record and detect on Mars.
You also developed an ultrasound technique to scan deep inside planetary bodies, which would be especially useful to determine whether Mars has a core. Do we know yet? Have there been any findings?
Yeah, it's a good comparison with the ultrasound, simply because seismic waves, when they're generated by quakes, they have the two components. You can think of it as P waves and S waves. So P, or compressional waves, are very similar to sound waves. So it's a fair comparison with an ultrasound, whereas the other class of waves is the so-called shear waves. The difference is that in the P waves, the motion is compressional, so the ground particles oscillate in the direction of motion, whereas in a shear motion, they oscillate perpendicularly to the direction of wave propagation. And so we have both on Earth and on Mars, we have both classes of P and S waves. That's a little bit different from stars, where we have only P waves, because shear waves do not propagate through liquids and plasmas. So we can use the propagation or understanding of how the wave field propagates through the interior to get some insights about its structure and dynamics. And we used the technique that we recently developed here on Earth, the so-called coda correlation wave field. And I will just briefly try to explain what it means. The coda means the late part of the waveform. So after the P waves and S waves and the surface waves, all these large waves are already passed. So the coda is almost like a tail, almost like the late part of the musical piece, if you want. So, but here we have a seismogram. And it's there mostly due to the scattering of energy, because when the seismic wave field propagates through the interior of Mars, it bounces off the boundaries, it reflects, it refracts, and we record this in the form of a tiny signals. So that's where the correlation comes in. Correlation simply means, in a non-mathematical language, it means a similarity. So we measured the similarity of these tiny wiggles many hours after the origin time of these Marsquakes. And what's really beautiful is that from the similarity of these tiny signals, we can actually get a signal. So the similarity of tiny signals becomes our signal. And in a way, it's more dominant than the large waves and the information they bring. So from the similarity of these late parts of the seismic wave field, we can infer the structure, the internal structure of a planet. And by looking at some of the signals in the so-called correlation wave field, we were able to detect the Martian core simply because these waves bounce off the core. And in a similar way to how the ultrasound works. And we were able to not only detect the existence of the Martian core based on these signals, but also measure its radius. Because, we can, simply speaking, we can come up with different models of the planetary interiors by enlarging the Martian core or shrinking it until the predictions match the observations. And when we did that, we established that the radius of the Martian core is 1,812 kilometers, which is um, which is pretty much halfway through the Martian interior. So the ratio between the Martian core and the Mars radius is very similar to the Earth's core and Earth's radius.
Well, we've been talking about Mars a little bit on Talking Science this year. What all of this information and all these press releases and all these studies have told me is that we really need to hurry up and get some geologist boots on the ground on the red planet very, very soon.
Yeah, look, there's still many unanswered questions about the Mars, and this for now tells us that Mars has a core, uh, which is probably liquid. We have not yet been able to detect the solid Martian core. So in that sense, if the Martian core is just liquid, it's different from the Earth's core because the Earth's core has a solid component. So namely, as the planet cools down, as the temperature drops at some point, the liquid component starts crystallizing and starts solidifying from inside out. And that's how the inner core grows, right? The solid inner core. So far, we have not detected the solid inner core of Mars. So what we know pretty much is just the size, and we can only infer again what that liquid core consists of in terms of chemical components. It most likely consists of iron and nickel, similar to the Earth's core, but the question is how many other light elements it might contain. And that turns out to play a critical role in the formation of the geodynamo that generates the magnetic field. And one of the biggest mysteries that is still unresolved is why Mars lost its magnetic field a very long time ago in its history. And that makes it different from the Earth because we know that the magnetic field protects the life on the Earth's surface from the cosmic radiation. So it's an important part of life. And we are trying to understand why Mars had such different initial conditions, or perhaps it started with the same initial conditions as the Earth. But what led to the cessation of its dynamo and the magnetic field? And to understand that, it's critical to understand its core It's critical to understand the core structure and chemical composition and the dynamic processes. So how quickly, for example, the core cools down, or what is the energy transfer across the boundary with the mantle, and so on. And seismology plays a very significant role in this understanding, because the seismic waves are pretty much our tool for in situ probing, if you want, of such a deep parts of the Martian interior.
Professor, thanks for your time.
Thanks for having me.
My thanks to Professor Tolcic for his time on this true deep dive. Would you like to watch more of these deep dives? Let me know in the comments. In the meantime, I'll be back for more Talkin' Science Daily Bites in YouTube Shorts, on TikTok, Facebook, Instagram and LinkedIn. Find us, like, follow and subscribe. Become a member too to get early access to our Monday deep dives, or whenever they happen during the week. It's all part of our 2025 commitment to bringing you science and space news and views with an Aussie flair.